Algebra 1, welcome to your 6th and 7th lesson in this video. What we're going to do is we're going to start with Lesson 6, and then after we're done with Lesson 6, we'll move on to Lesson 7 in the same video. In Chapter 1, Lesson 6, we're going to talk about relations. So our objective is to represent relations, and we are interpreting graphs of relations. The standards that we're going to be talking about is Standard IF1, which means functions, interpreting function standard number 1, and then algebra, reasoning, equations, and inequalities standard number 10. These are the two standards that we're really going to be addressing in this lesson. So let's go ahead and on the next slide, go ahead and copy down your vocab. It's actually going to take 2 slides, so make sure you pause the video, copy down the first set, pause the video, copy down the second set. One of the first things we're going to do is we're going to take a bunch of coordinates and we're going to express them in 3 different ways. So we have to express them as a table, a graph, and a mapping. So what we're going to do is we're going to start with the table and a mapping, and I'll show you how those work. When making the table, what we got to do is we got to be able to identify ordered pairs. And in an ordered pair, you actually have 2 values. You have the x value and you have the y value. So the very first number that you see, that's your x value. The second value you see, that's the y value. So whenever making a table, what you want to do is you want to start with like a T-chart. Put x on one side, put y on the other. And we can actually make this look like a table. All we got to do now is label what's my x's and what's my y's in the table here that we're going to be making. So my x value is 4 and my y value is 3. When you make a table, you want to make sure that your x value matches the y value that goes with it. Because what you're really doing is you're creating a relationship between the two. -2 is going to be paired with -1. And since the first number we see is an x, the second number is a y, that means -2 goes here and -1 goes here. 2 is an x and -4 is a y. And then finally, we have 0 and -4. Again, 0 is an x, and -4 is a y. Now, I'm going to take it, put it in a box, and what we just did was we made a table. So to make a table, all you got to do is have x's on one side and y's on the other, and you're separating the two, but you pair them up together based on what happens in your relations. So the first thing we're doing is we make a table. So here's my table. I'm even going to write, this is what a table looks like. Now, one of the easy ways to explain what a map is a map tells you directions. So we're going to kind of make it look like we're learning directions here. I'm going to use these same x values. I'm going to put them inside a circle, well, an oval, kind of like this. So this is what a map would look like. I have 1, 4. I have a -2. I have a +2, and I have a 0 on my x values. Then I'm going to make another oval here, and I'm going to call these my y values. And my y values, I have 3 once, I have -1, and if you see you have -4 twice, you only have to write it 1 time. Because what we're going to do is we're going to create a map. And in a map, it's kind of like Google Directions. What you're going to do is you're going to see how it goes from one place to another. So 4 is paired with 3. So notice I put the arrow going to 3, which says this is the direction that 4 is going to go with. -2 is going to go with -1. +2 is going to go with -4. And 0 is going to go to -4. So what happens is we can create a map by showing what pairs with what kind of directionally. And that's one of the things that makes it kind of easy to understand, is a map tells you directions. So you're kind of telling each other directions on how to get from one place to another. Now, if you have a repeating number, like we had -4 come up twice, you only have to show that both numbers go to that number 1 time each. So this is a table, and this is a map. The last thing we have to do is we have to take these coordinates, and we wrote it as a table, we wrote it as, not a graph, but we wrote it as a map. Now we have to make this a graph. Okay, so to make this a graph, you can make the graph big, you can make the graph small. I'm going to make it fairly large so you guys can all see it in the video. So what I'm going to do is I'm going to erase this. I still have the information up here, and I'm going to show you how to take that information and make a graph with it. When told to express this as a graph, what we want to do is we want to actually go ahead and start with two lines, one vertical line and one horizontal line. The horizontal line, based on our definition, is going to be called our x-axis, so it's important to label it with an x. The line that goes vertical is our y-axis, so it's important to label it with the y. When you make a graph, sometimes you end up with two lines and they don't have any marks on it, so it's kind of hard to determine what's happening. It's your job to put marks on your graph. What you want to do is you want to try to put equal spacing in between. So you try to eyeball it. Make sure that when you're putting lines on it, they're just about equal distance based on what you can perceive to be correct. Sometimes you can get very technical and you can actually use a ruler to make sure that all of your lines are the same, and that's okay. But in this case, you really don't need to do that. What you just need to do is try to make it so that it looks like the spacing between everything is equal. Now, when making a graph, you have your marks, you have the x line and the y line labeled, so you want to make sure that that's there. And now you're going to use your coordinates, which are what's already given to us in the problem, and you're going to graph those. Coordinates are awesome because coordinates are just like your maps. They tell you directions. The first number tells you which direction to go, right or left. If that first number is positive, that means your graph is going to move to the right. If that first number is negative like this, that means your graph is going to move to the left. If the second number is positive, that means your graph is going to move up. And if your second number is negative like this one, that means your graph would move down. Now the point that you have to start when graphing is you always want to start at the origin. And the origin is this little point right here. So this is your origin. Your origin is right where your two lines connect. Now, normally you don't put a mark on the origin. I'm just putting a mark on the origin to show you where the origin is. And the coordinate pair where the origin is 0, 0. Anytime that you're graphing, you always want to start at the origin. So what I do is I use my finger. I start at the origin. Now, I'm going to look at my relations. In my ordered pair, I see I have a 4 and a 3. Well, the 4 is the x value. So I'm going to go to where 4 would be on the x line. 1, 2, 3, 4. So I'm right here. Now, the 3 is my y value, so I need to go where 3 is on the y line. But I'm right here at 4, so I go 1 up, 2 up, 3 up, and I put a dot. So at 4 over, 3 up, and that's my first point. I got that from my directions here. 4 to the right, because that's a positive 4, 3 up, because that's a positive 3. The second coordinate is a negative coordinate. So again, you start at the origin, you go back to 1, 2, and since that's a negative 1, you would go down 1 and put a dot. So this is where the second coordinate would be. The third coordinate says 2, negative 4. So you start at the origin, you go over 2, that's a negative 4, go down 1, 2, 3, 4. So right now, we have 3 different points on our graph. The final point that we got to do is 0, negative 4. So we start at the origin, and now we go 0, right or left. So we don't go right, we don't go left because it says 0, but it does have a negative 4, so we're going to go down 1, 2, 3, 4. This is all we have to do to graph. The ordered pairs, or the relations that we have, tell us which direction to go. The first number tells us right or left, and the second number tells us up or down. So hopefully you're understanding that. We're going to practice it a few more times, but before we do that, I want to talk about your other words that are in your vocab list, domain and range. So what we're going to do is we're going to take these ordered pairs and we're going to identify the domain and we're going to identify the range. Continuing on with example 1. In this part of the problem, what we're going to do is we're going to identify the domain and range, so based off our 2 vocab words. And if you remember, our vocab words say that the domain is all of the x values that are present in the problem, or all the x values in the relation. So in this case, our domain is only the x values. So domain is only x values. That's the thing we need to remember. So what we do is we look at all four of our relations, and we say, what's in the spot of x? Well, in the first relation, or first ordered pair, 4 is in the spot of x. In our next ordered pair, -2 is in the spot of x. In our next ordered pair, 2 is in the spot of x. And in our last ordered pair, 0 is in the spot of x. So our domain is 4, -2, 2, and 0. These are all of the x values. So hopefully you're thinking that if domain is all the x values, then range is all the y values. And you're absolutely correct if that's what you're thinking. So let's go ahead and write the word range. And that's only your y values. So what you do is you look at all these relations or ordered pairs, and you write down only the y values, and that's your range. So 3, -1, and -4. And I don't think I have to write -4 again because I've already got -4. So I'm going to go ahead and just leave it like this. So if we have a number repeat, we only have to write that number one time. So my range is 3, -1, -4. That's because they're all the y values. And if we have a repeating one, we only have to write it once. My domain is all the x values. 4, -2, 2, and 0. None of those repeat, so we did write all of them down. Let's move on to another example. In example 2, what we're going to do is we're just going to take a bunch of coordinate pairs and we're going to express it as a mapping and a mapping only. So think about how we did the map in the first example. Remember that we started with two ovals. We start with our x values and we start with our y values. Now, what you want to do is put all the x values in the first oval and all the y values in the second oval, and you want to identify which one goes to which one using arrows. So my first x value is 3, my next x value is 4, 5, and -1. My y values is -2, 6, 2, and 3. And remember, I know it's a map because it tells me that I have to do directions. So since it tells me I have to do directions, all I got to do is pair up these ones, which one they align to. So this is how you do a map given the situation. Remember that a map tells you directions. A table looks like a giant box with everything on one side and everything on the other. Continuing on with example 2 in kind of another way. What we're doing is we're taking the same coordinates that we just had, and now we're determining domain and range. So domain, I'm just going to use the letter D for domain. My domain is all the x values, 3, 4, 5, and -1. My range is all the y values, -2, 6, 2, and 3. So just a quick reminder, domain, all of the x values, the ones that we see first. Range, all the y values, the ones that we see second. And all you got to do is label which goes in which group. In example 3, we're going to talk about a story problem. In this story problem, we're going to talk about temperature and electricity. So it says, in warm climates, so in hot areas, the average amount of electricity used rises as the daily average temperature increases, and the amount of electricity used falls as the daily average temperature decreases. Our job is to identify independent and dependent variables. Now remember, an independent variable is the one that doesn't need the dependent variable to kind of work, where the dependent variable changes based on the independent variable. So what I have is a little trick that we can use. Blank depends on blank, blank depends on blank. Go ahead and write those two statements down. Blank depends on blank, blank depends on blank. Now the two things that are changing in this problem are electric and temperature. So we're going to write those two words on the blanks. Electric and temp. Temp and electric. So what we did was we switched the two words the second time we write it. So the question is, does the amount of electricity we use depend on the temperature outside? Think about that for a sec. Or does the temperature outside depend on the electricity that we use inside the house? So the temperature that we have outside changes based on what electricity we're using in here. So think about that and figure out which one of these sounds correct. Hopefully you guys are all thinking that the top one sounds correct, and that would be correct. The amount of electricity we have depends on temperature. Since electric depends on temperature, that means it's our dependent variable, which would make temperature our independent variable. And so what that really means is we really don't change temperature. Not too much. The temperature outside does not change based on the electricity we're using in a house. The electricity we use in a house will change, though, based on the temperature outside. If it's cold, we might use more heat. And if it's hot, like this climate, we might use more air conditioning, which will mean that our electricity goes up. So, a trick to finding out independent and dependent variables is blank depends on blank, blank depends on blank, and then ask yourself, which one relies on the other? Let's go ahead and do another problem. In example 4, we're going to do another independent and dependent variable situation. So in example 4, it says the number of calories you burn increases as the number of minutes you walk increases. Identify the independent and dependent variables for this function. So what we have to do first is identify the two different things that are happening in this function. So it says the number of calories you burn increases as the number of minutes you walk increases. So the two things that are changing are the calories and the minutes. So these are my two variables. Do calories depend on minutes, or do minutes depend on calories? So if you're reading this problem, again, it says the number of calories you burn increases as the number of minutes you walk increases. So in this case, hopefully you're thinking that the amount of calories that you burn depends on the number of minutes that you're walking. Not the number of minutes you walk depends on the number of calories you burn. The amount of time that passes doesn't change your calories. It's the calories depend on how long you're walking. So calories are depending on the time, where time does not depend on the calories. And one of the things that you'll learn is almost 90% of the time, time is always an independent variable. And independent variables, just so you know, are always on your x-axis. Kind of piece of advice you'll need for later. So minutes are your independent variable, where calories are your dependent variable. So I am able to say that calories depend on minutes. The amount of calories I'm going to burn depends on how long I'm walking. Not how long I'm walking depends on how many calories I'm going to burn. So our answer for this one is the top sentence. Let's go ahead and keep moving. In example 5, we're going to look at something called a qualitative graph. And a qualitative graph, notice it's a graph that doesn't have any numbers. What we're going to do is we're going to try to think about what's happening in the situation and maybe try to explain it. So it says the graph represents the temperature inside a classroom on a winter day. Describe what happens in the graph. So here's our graph. We have to describe what's happening in the graph. This is the temperature inside the classroom, and this is time. Time is always going to be moving forward, so the graph is always going to be moving forward. And the temperature in the classroom is always going to be changing, so we need to think about what might be happening. At the very start of the day, what's happening is the temperature is going up. So think about a classroom. Why might the temperature be going up at the start of the day? Hopefully, you're thinking about the fact that a teacher might be turning on the heater, so that way the room starts getting warm, so you guys are nice and cozy in the classroom. So, the teacher turns on the heater. That's one of the things that we could talk about being the first thing that happens. After the teacher turns on the heater, what happens is when the temperature reaches a certain point, that heater is actually going to turn off nowadays. What that means is it's going to hit where the thermostat says, okay, you've hit the temperature you want to be at, and now we're going to shut off. And what it's going to do is it's going to allow the heat to go down. And then the temperature is going to go back up. So the thermostat is going to keep fluctuating the temperature in the room until about the end of the day. So the teacher turns on the heater, and the thermostat thermostat will actually keep the temperature in a certain range. What happens is, once it gets to the point, it shuts off, lets the room cool down a little bit, then it'll turn back on and bring the temperature back up to where it needs to be. So it's never going to get too cold in the classroom because the thermostat doesn't allow the temperature to do that. So the teacher's going to turn on the heater. So that brings us right to here. The thermostat's going to keep the temperature in a certain range, which means it's going to allow the temperature to drop and go up, drop and go up, drop and go up, drop and go up. But what's happening here? Why might the temperature in the classroom continuously go down? Hopefully you're thinking about the fact that it's the end of the day and we turn off the heater, because we don't need the heater to run when nobody's in the building. So, the teacher turns off the heater for the end of the day. So one of the things that we have to do in this lesson is we have to kind of think about what's happening in a graph without actually seeing numbers and kind of judge what could potentially be happening that makes some type of logical sense. Teacher turns on the heater fluctuates based on the thermostat, temperature goes down because teacher turns off the heater. Let's try another problem that deals with qualitative graphs. In our last example for lesson 6, let's try this again. In our last example for lesson 6, example 6, we have one more qualitative graph that we're going to talk about what could be happening in the situation that's given. So again, this is kind of theoretically what could be happening based on what we see in the graph. It says the graph represents JJ's speed as he swims laps in the pool. Describe what is happening in the graph. So we have to describe what's happening. If we look, the speed is going up and the speed is coming back down. Speed is going up. And speed is coming back down, speed is going up, and speed is coming back down. So think about swimming a lap in a pool. The speed might be going up as you cross the length of the pool. So, you would say JJ is speeding up across the length of the pool as he swims. So as JJ swims across the length of the pool, he would be speeding up. Why would the speed be going down though? As he gets close to the side, he don't want to go too fast because he don't want to run into the wall, so he's going to actually slow himself down before he gets to the wall. So the speed is increasing or speeding up as he goes across the length of the pool. Then he starts slowing down. When he approaches the wall. So once JJ approaches the wall, this is where his speed is going to be at. He's going to be at 0. He's going to speed back up as he goes back to the next round. And the process continues. So in this problem, what could be happening is JJ speeding up, speeding up, speeding up. Now he notices he's getting close to the wall, so he's going to start slowing down. He reaches the wall. He now has a speed of 0 because he just hit the wall. Now, as he turns around and he starts swimming back across the pool, his speed's going back up, and then it starts slowing down as he approaches that wall. And it just keeps going. So this could be what's happening based on the situation if you were swimming laps in a pool. So remember, a qualitative graph is a graph that has no numbers, but we can still think about the situation and kind of give meaning to that situation. So we're going to describe what could be happening. Now, you need to make sure that it does make sense and it could be logical, because if it's not logical, you're not going to get the answer correct. That's it for lesson 6. We're going to go ahead and move on to lesson 7. Make sure you guys got everything here. And lesson 7 will be a little bit shorter than lesson 6. Let's keep going. So, continuing on with chapter 1, lesson 6. Now we're on chapter 1, lesson 7. In Chapter 1, Lesson 7, it's going to be a little bit faster than 6 was. This one's going to be all about something called functions. Our objective is to determine whether or not a relation is a function. So why I'm combining these together is we just learned what relations were. That's where you pair an x value with the y value. Now we're going to determine whether or not a function exists between them. So we're going to learn what a mathematical function is and whether something exists. We're going to find function values too. So that means we're going to plug something in and we're going to get something out of our function. Because if something functions, if we put something in, we'll get something out. The standards we're going to be addressing is standard on functions, interpreting functions, standard number 1, and standard on functions, interpreting functions, standard number 2. Let's go ahead, get started on this lesson 2. Alright, so you guys just copied down all of our vocab words for this lesson. Yeah, it's about 6 or so vocab words. That's okay. Here's a little bit more of the idea of what a function is. So this is a better definition of what we can define a function as. A function is a relation, which means that we have an x and y, that is paired together in which every x value, and notice I underlined the word x value, is paired with exactly one. Now I double underline, I pointed an arrow. You're only allowed to have one y value. So a function is where every x is only paired with 1 and 1 y value. So 1x to 1y, 1x to 1y, 1x to 1y, 1x to 1y. So this is a look at a map, but this map is a function because every x is only paired to 1y. This is also a function. It might not look like a function to you, but this is a function because in this problem, what we have is it's a test that we can do to determine if this is a function. We have a test that you guys just copied down on vocab, and that's called the vertical line test. What a vertical line test means is that if I draw a line straight up and straight down, I'm only allowed to hit a graph at one spot. I hit this graph at this one spot and this one spot only. This means this graph passes the vertical line test. If you draw a line straight up and down as many times as you want, and every time you draw a line straight up and down, you only hit the graph one time, then this would be a function. Because every x value is only paired to one y value. So anytime you draw a line straight up and down on a graph, if it only hits one time, that's a function. If it hits 2 times, that's not a function. So in a map, 1x to 1y, in a graph, do the vertical line test to test if you have a function. In our first example, what we have to do is we have to look at this map and determine whether or not it's a function. Not only do we have to determine if it's a function, but we have to state how we know if it is or isn't. That's what it means when it says explain. So, we have -2 going to -8. We have 0 going to 0, 2 going to 8, and 4 going to 16. So in this case, this is a function. So what you do is you say, yes, it's a function. Because every x goes to only 1 y. Because in a function, we know that every x value is only allowed to go to 1 y value. So this is a function because every x goes to exactly 1 y. There we go. Let's try another one. In example 2, we have to determine whether or not this table is a function. So what you want to do is you want to think about the rule of a function. Every x value is paired with exactly 1 y value. So we look at this. Domain is the x value. Range is the y value. 1x to 1y. None of them repeat. 1x to 1y, 1x to 1y, 1x to 1y. So in this case, this is a function because x doesn't repeat. That's not allowed. X is not allowed to repeat. But y can repeat and we'll still have 1x to 1y. So in a function, you're only allowed to have 1x to 1y. Not the same x to 2 different y's, but 1x to 1y. So you'd say, yes, this is a function. 1x goes to 1y. That tells me that you understand how this is a function. Let's keep going. In example 3, we have another table, and this time instead of domain and range, we have x values and y values. And we have to determine whether or not a function exists. Reminder, 1x to 1y. So, we have 1x, which is 3, to 2. 1x, 1 to negative 2. 2 to negative 4. Now look, 3 came back up. So that means the x value of 3 is happening twice. So this means that our 1x value of 3 is coming up more than once, and that's not allowed. So this is not a function because we do not have 1x to 1y. So you would say, no, it's not a function because 3 is paired with 2 and negative 1. So we know that this is not a function because the number 3, which is 1x value, is paired to 2 different y's. And in the rule, we're only allowed to have 1x to 1y. Let's go again. So it says determine whether or not this relation is a function. So what I have is I have a discrete graph. A discrete graph is a graph that's not connected by lines. So this is a discrete graph because what it is, this is a graph that's broken up. So in this graph, we have to determine whether or not this is a function. Now remember, in order to be a function, it has to pass something called a vertical line test if it's graphed. So what you do is you draw a line straight up and down through every point. Now, if your line only hits each one of those points one time, then it's a function. If it only hits twice, then it's not a function. So you want to see how many times is it hitting each one of these marks every time you draw a line straight up and down. Since we only hit one time, that means this is a function. So what you do is you say, yes, it's a function. It passes the VLT. Now, VLT stands for vertical line test. This graph is a function because it will pass the vertical line test. And you can do it with a discrete graph or a continuous graph. A continuous graph is a graph that's connected. A discrete graph is a graph that's disconnected. So what's happening is we draw a line straight up and down and we say how many times does it hit in the graph. If it hits 1 time, it passes the vertical line test, it's a function. If it hits 2 times or 3 times or 4 times, it doesn't matter how many times it hits, it's only allowed to hit 1 time. So if it hits any more than 1 time, it's not a function and therefore it will not pass the vertical line test. Let's go ahead and move on to the next part. In example 5, what we're going to do is we're going to look at 2 different graphs and determine whether or not either graph is a function or not and explain. So in our first graph, which is this blue graph here, we have the green line that goes up and down. Our job is to determine whether or not this graph right up here is a function. So what we have to do is determine, does it pass the vertical line test? Well, in this case, it is a vertical line. Now, what you have to remember about a line is that it's made of many different points. So on this line, there's actually a point here, 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 here. There's tons and tons of points on this line. So if you think about the vertical line test, are you only hitting 1 point if you draw a line straight up and down? Since you answered no, this does not pass the vertical line test. So therefore, it's not a function. Now, if we had a graph that went straight left and right, and we drew a vertical line up and down, we only hit this graph 1 time, 1 time, 1 time. So every time that we draw a line straight up and down, we're only hitting the graph once. Therefore, this does pass the vertical line test. So it passes the VLT, which means it's a function. So if we have a graph that goes straight left and right, that's a function. If we have a graph that goes straight up and down, that's not a function because it doesn't pass the vertical line test. Let's move on to actually plugging numbers in to function notation. In example 6, we're going to start talking about function notation. Now, functions are where we plug something in and we get something out. Hopefully you've seen function notation maybe in 8th grade. If you haven't, that's okay. I'm going to cover it through this lesson here. But when you read function notation, this is a problem written in function notation. It says f of x equals 3x minus 4, or 3 times x minus 4. They want us to find the function of 4. So when you read this, notice I read it as the function of x, or f of x. What that means is this is actually taking the place of the value of y. F of x is just another fancy way for saying the letter y, or the range, because y is range values. So what that means is we're going to plug a number in, and we're going to get a number out. What function notation allows us to do is it allows us to see what number we plugged in, and then it tells us what number we get out at the very end. What we're going to do is we're going to look at this problem here. It says the function of x equals 3 times x minus 4. Our job is to find the function when we plug in 4. So notice that 4 is now in the spot of x. What this 4 means, since it's inside parentheses, is inside parentheses, we're going to plug the number 4 in for whatever's inside parentheses here. So 4 goes here. Well, that says x. Since we see an x there, we're also going to put a 4 there. So what you would do is you would say f of 4, notice I replaced x with 4, and that's because we have 4 here. The function of 4 equals 3, I'm going to put this in parentheses, 4, because again, inside parentheses, we have 4, and that's taking the spot of x. We said x is 4, minus 4. Now, the reason why I put this x inside parentheses is it's not the number 34. We have to remember that a number next to a variable means multiplication. So this is 3 times 4, and then we're taking away 4. Now, when you do function notation, the left side is never going to change. The right side is going to change, and we're going to figure out what number we plugged in and what number we get out. So this says that we plugged in the number 4. Notice the number 4 is now in our problem. So the function of 4 equals 3 times 4, that's 12, minus 4. So all I did was solve another piece. I took 3 times 4 and I changed it to 12, which means we did substitution. The function of 4 equals 12 minus 4, which is 8. The cool thing about function notation, to me, is that you know what your x value is because that's the number you plugged in. It's called your input. And now you know what your y value is. That's the number we get out. So what we're able to do is we're able to take our function notation and get a coordinate pair, which means if we had to graph that, we could graph that the coordinate pair is going to be 4, 8. So function notation tells us what number we plugged in, and on the right side, it tells us what number we get out. So when we plug in 4, we're going to get 8 out in this problem. Reminder, whatever's in parentheses is what you're going to be plugging in to your problem. Let's go ahead and do another problem and see where we're at. In example 7, we're going to be finding a function that has us plugging in -5, but adding 6 at the end. The number that's inside parentheses is the number we're going to plug into the problem, and the number outside the parentheses is something we're going to add to the end of the problem. If it's inside parentheses, we plug it in. If it's outside parentheses, we put it at the end. So it says if f of x equals 3x minus 4, we're going to find f of -5, but we're adding 6. So we start like we did the other one. F of -5, but in this case we're doing f of -5, and we're adding 6 equals 3. Notice that the number inside parentheses is -5, so here's an x. We're going to put -5 minus 4, and now since we have plus 6 on the outside, we're going to put plus 6 at the very end of this problem. So all we did was replace what's inside parentheses with the letter x, or the variable x, and then we added 6 at the end because 6 is on the outside, so it's not going to replace our variable. Only what's inside parentheses replaces the variable in the problem. So f of -5 is 6. We rewrite that again. F of -5 plus 6 equals 3 times -5. That's -15. Minus 4 plus 6. All I did was solve this part here. 3 times -5, that's -15. So I'm solving this problem slow. I'd rather solve the problem slow and then change it to something different at the end. F of -5 plus 6 equals a -15 minus 4 is -19. And then we're adding 6. So again, I just combined those two things. The last thing I got to do, f of negative 5 plus 6 equals, and now we just figure out what negative 19 plus 6 is. And negative 19 plus 6 is negative 13. And this would be my answer to my problem. When I plug in negative 5 for the x value and I add 6 at the end, I'm going to get negative 13 as my final answer. In example 8, we're going to be doing another function problem. This time it says if f of x equals 2x plus 5, find f of 3. So this one's a little bit easier. All we're doing is replacing 3 for our x value and solving. So we rewrite our problem. F of x equals 2x plus 5. Now we're going to plug in f of 3. So f of 3, notice that x is being replaced with 3, equals 2, there's an x, I'm going to put it in parentheses, 3 plus 5. So what this means is I have 2 times 3, and I'm adding 5. So f of 3, or the function of when I plug in 3, equals 2 times 3, that's 6, 6 plus 5. So the function of 3 equals 11. And again, this is the number we plug in, this is the number we get out. So our answer is this right here. The function of 3 equals 11. Let's do one more problem and call it a day. In this example, we're going to do something similar to what we just did. What we're going to do is we're going to take the function of 2x plus 5, but this time we're going to find f of negative 8. So what I did was I already rewrote the problem. We're going to plug in the number that it tells us to plug in. We're plugging in negative 8 anywhere we see the letter x. So, or the variable x. We have f of negative 8 equals 2 times negative 8 plus 5. Well, the function of negative 8 equals 2 times negative 8, that's negative 16 plus 5. The function of negative 8 equals a negative 16 plus 5 is negative 11, and that would be our answer. You guys did awesome today. I know this was a longer lesson because you had 2 back-to-back. Hopefully you got all your vocab done for both lessons. Hopefully you got all the slides. I know you guys did awesome. I'll see you tomorrow. If you haven't, go ahead and like this video. Click that thumbs up. Make sure you hit that notification bell. And if you haven't yet, go ahead and subscribe, because you want to be able to get these videos anytime I post them. I know sometimes they'll be posting late, but you guys are going to get them, and you guys get time to do them. Make sure you have them done. If you don't have them done, you'll do them in class. I need to make sure that you have your notes so that way you guys can always do well on your quizzes.